Thanks very much. As you heard, I'm Nathan, and I've been using Go now since about 2013. I made the switch back then from Java, and frankly, I've never looked back. So I then played a part in our team's adoption of Go as one of our main development languages, where I work at Turnitin. We're an edtech company. We specialize in plagiarism detection and assisting students with the writing process. But in order for us to detect potential cases of plagiarism, or as it's more formally called, identify an original source material in student submissions, we need to have a large store of papers, journals, books, web pages, that sort of thing for us to be able to match against. And I work on the team that's responsible for bringing that content into our proprietary index and is also responsible for generating reports based on that content. Now, in software at the moment, it seems like monolith is something of a dirty word. Now, if you happen to mention, oh, I'm working on a monolith, which incidentally I am, you get responses from pity, the sort of, oh, maybe you can work on something cool later, through to expectation, the sort of, oh, but you're going to move that to microservices and that'll be exciting, won't it? But there are cases where, you read examples of, you should move from the monolith. Don't start with a monolith. Break everything up. And I guess web applications with large amounts of traffic and clearly defined areas of responsibility that can be composed by the user or the consumer, that makes a lot of sense. That's really good advice, and microservices are great in those contexts. But there are applications that are not like that. And I believe that our software solutions can easily become overly fragmented and the boundaries of clear concern lost in unwritten interdependence. And I've seen that played out over a number of years in a variety of domains across a variety of languages. Architectures that then confuse the difference between fragmentation and orthogonality. They cause problems for both the code and the engineers. I think we need to consider sometimes the benefits of reducing, simplifying, and minimizing our architectures with a less is more mentality. So, why has that not worked? There we go. Before we go any further, though, we should really define monolith. As the design philosophy is that the application is responsible not just for a particular task, but can perform every step needed to complete a particular function. So to put it another way, a monolithic application is one which takes care of an entire process from end to end, handling every step in that workflow. And drawing on recent experience of migrating a largely fragmented architecture, I'll show that Go provides us with the constructs to reduce the number of services and moving parts that you need, while maintaining a clear separation of concerns. So what follows next is a true story. It's a recent story, and it's one that bucks the trend. Now, before we dive into the story of why and how we built a monolith to solve our problem, there's a couple of key terms that I just need to define for you so this whole thing makes sense. So first of all, we have a provider. A provider is basically an organization or a publisher or possibly a group of publishers that gives us content items to ingest and index. Now, an item is an actual piece of content. It's the book, it's the chapter, it's the journal, along with any metadata, such as the title, the author, when it was published, where it was published, all that sort of information. We have to pull all that in and index that, ready for matching against. So, with those terms in mind, here's the legacy stack. And this is the basic architecture diagram. I know, take that in for a second. It's awful. It's our essential problem statement. This was responsible for ingesting our non-public content. So not stuff that's on the web and freely available, but stuff where we have partnerships with publishers and providers. Now, as I say, despite the complexity of this diagram, and it still makes my head hurt a little bit thinking about it, this is our basic overview of that stack. There's so much more to the process. There's more sources of data, there's more apps, there's more data stores than I could realistically show you all on one slide. But as a quick rundown here, the boxes at the top, those red and purple ones, they represent remote disparate collections of vaguely related data that we need to ingest. All the rectangles then, those are application scripts or crons in the process of retrieving, parsing, and indexing all that data. And then each stage of that is kicked off either manually, like literally you go to the command line and you type in the command to fire something off, or it's run on a cron, or it's an HA long-running app. And we use databases as queues as well in this architecture, just to really nail home the horror of this. So, as you can see, though, it's hard to hold that high-level abstraction in your head. Those rectangles as well, they typically were more than one per data source. So the architecture and data flow of each of those processes, or each of those apps, is another level of detail you can't possibly hope to hold in your head. You can't memorize what's going on inside all of that. I've not even named the apps on the diagram. Frankly, they don't add any clarity, they just make it all worse. But put it another way, I gave a 30-minute talk just on this to people I work with who are supposed to already know half of it. And you're all spared that today, thankfully. We're not going to do that to you. But one word for this architecture is fragmented. You know, there's lots of different apps and services doing lots of different things, also doing lots of very similar things. But this is fragmented. This is the same level overview of the new system. Well, that's much simpler, right? That's much easier to reason about. As you can see, we still have all the data sources. There's still different file types. There's still different formats. I'll admit, we worked with some of our content providers and said, hey, you got to help us out here. You know, we'll simplify what you're doing a little bit. I mean, as an example, one of the providers in the old architecture gave us 4, I think it was, spreadsheets via email on an ad hoc basis, and then a multitude of XML files on FTP on another ad hoc basis, and you had to pull all of that together to make the clear picture. So, you know, we simplified that down to an XML feed that has a sort of standard protocol that we use. But, you know, it's still XML. We tried for other things, but there's no move in some people. We can also then, with this, easily display the data flow through the system. And most importantly, the data flow is now consistent for all of our providers. But this is what makes it a monolith. This is a single application that defines a complete workflow. We could have taken all of our other components, if you like, all the stages of this workflow and broken them out into microservices. And that would have brought us clarity over the old architecture, for sure. But I don't think it would have been the right choice. It would have introduced some extra complexities, you know? Microservices are not a free lunch. So if we briefly consider that alternative, because that's what we did, you can see that using microservices for this pipeline would have brought us greater complexity. This alternative approach adds more components, it adds more technology, it adds more layers for us to manage. The communication approach such an architecture would use, whether that's REST or gRPC, that would have increased the latency between the components compared to simple function calls and channels, which is what we are using. Now, under this alternative, we would have been able to spread work out across the cluster. We would have been able to scale it horizontally, independently of one another, all that good stuff we could have done with this. And that all sounds really nice. But we don't actually need that for our application. It's not something that would benefit the workflow we're doing. So the further drawback to this is that we end up with more complex configuration, more complex deployment, more complex testing, whereas under the monolith, you deploy a whole thing. You test the end-to-end. It's very simple to test the full pipeline. And we can deploy it all in one go with just, you know, one YAML file for configuration. I don't know if you've used Kubernetes, and I love Kubernetes. We do deal with microservices, and it's great, but there's a lot more YAML in dealing with Kubernetes than there is with deploying this. But you know, the configuration, as I say, is done with one YAML file, and then you just restart the app, and you're up and running. It's very easy, but it's benefits for our context. That's the important part here, and they were worth pursuing for us. So, while both microservices and the monolith need to have clearly defined pipelines, and they need to have well-focused areas of responsibility, there are trade-offs in each choice. As you can see here, there are some key comparisons we looked at in making our choice. Now, picking up on a few of these, we decided that for us, the use of channels, as we'll see shortly, was the best way for us to define the pipeline. We traded off distinct services and horizontal scaling for clarity of data flow and simple in-app scalability. I think the biggest drawback of this choice of choosing the monolith is that we now have to have the app all on or all off. And there have been times where being able to turn off one part of it and leave another part running would have been really helpful. But that's been a small price to pay for the simplicity we've gained. And simplicity that comes in our code, it comes in the testing, it comes in the configuration and the deployment. The final main benefit for us in this application is that Go's packages, the package structure that you have, has enabled us to share code within the monolith very simply. It's certainly easier than some of our other projects where we have microservices vendoring in a shared common library and updating that across all of those repositories. It's worthwhile sometimes, but it's also a bit of a pain. So, having defined our problem, outlined the solution we chose, and sort of detailed why we picked that, here's what made it all possible for us. Some key concepts from Go that within this architecture allow us to deliver a cohesive application whilst retaining our clear boundaries. And that's interfaces, Go routines, and channels. I'm going to look at each of those and sort of demonstrate how they've helped within our project. So interfaces. These are a key part of understanding Go code and writing clear Go code. You need to understand interfaces, and what follows next really is how we've leveraged their power rather than an explanation of how they work. So hopefully we'll all be able to follow along here. Now, within the ingest of content, there are numerous types of provider. As you kind of got the hint from the basic architecture, lots of different boxes doing lots of similar things. Those are the different kind of provider types. How they format data, how they provide the data, all that sort of varies, but what we want to do with it is process it. So while there's as many different data standards as there are publishers available to give us data, we can still now process things consistently. So we have this single method interface that allows us to handle that very easily in code. It's a simple interface here that acts like a clear contract for this stage in the workflow. And it provides us with guarantees on what's going to happen in this step. So when you call the process method, you know you're going to deal with a particular provider, and you know that that process is going to put items on a channel. It's not going to take them off, it's only going to put them on, because that's what the contract says. So with this interface defined, we can have a manager struct. This manager controls the whole process. It's our kind of brains of the operation. And it needs to know about each of the processes that we have in use. But by using the interface type, we're making certain guarantees about what processing will look like. This allows us to simply call process, making for cleaner code. Now, we can still support the plethora of data standards and the multitude of retrieval mechanisms that all these different providers give us, but we can do it clearly in one application. And the process details remain distinct, but we don't have the fragmentation that we once had. So when processing needs to happen, we know that there's a process method because the member or manager is of that interface type. We know then that it will always populate the item channel, and it will satisfy our internal contract for data flow. Now, using the interface allows us to craft a manager that has what it needs without needing to know about implementations. So in this particular case, it also simplifies or dries up any error handling we want to do. And this keeps our boundary of concern. The processors are responsible for processing, and the manager simply knows to invoke that part of the pipeline. But you compare this with the previous architecture, under which we had distinct apps or services or scripts for different content providers. Well, we still have correctly scoped responsibility, but we can still have distinct providers being processed simultaneously, but we don't have to manage distinct code bases or distinct running processes anymore. That's a big win. If we'd done this with microservices, I think we would have had a processor interface that's worked fairly similar. But the communication between stages would have become more complex than just a simple set of Go routines using shared channels. Those things are very simple and they give us great power. I'm just going to, if you excuse me, I've had a bit of a cold this week, so I'm just going to have a little drink. We also use interfaces as parameters to functions. So we have an interface definition that defines the required consistent behavior for parsing delimited files, things like XLSX files and CSV files, that kind of thing. And having this interface enables us to keep such processing grouped together. It's all in the right spot now, in accordance with our definitions of provider types. So we want to handle what we call our independent providers in one processor. And typically the only difference is that they give us either XLSX or a CSV. We don't need to break that up at all. So having the interface to handle the behavior allows for simpler handling of the data, and it means we don't need to fragment our independent providers like we once did. So if you recall from the basic architecture, those purple boxes particularly, each one of those was a different data provider, a different source. It also meant a different custom script to process each of those different sources. And sometimes even a set of applications were used. But here, as you'll see, we don't need that fragmentation anymore. So in use, with the parse function here, obviously trimmed down to fit somewhat, but it just takes this spreadsheet type. So depending on the actual type of metadata we're dealing with, we get the correct implementation. But it's of that spreadsheet interface type. And this means that parse is focused on just creating content items out of the raw data. It has its clear focus. The implementations of the interface take care of all the file-specific needs for extracting data from that format. So we have our clear bounded concerns. We have orthogonality, but we have no fragmentation here. Another great use for interfaces, as I'm sure many of you know, is injection. Again, that will help you keep clear focus. processors, in our case, need to go and fetch data from third-party servers. And we need a standard definition of what fetching looks like. So, things like timeouts are correctly and consistently defined, and things like the user agent string, that's consistent across all of our fetching, which is important because a number of our providers rely on our user agent string being what we've said it will be, so it has to be right. Now, injecting a fetcher into the processor simplifies that. It also means that processor, which needs to fetch, doesn't need to know anything about how to fetch. It can just call the fetch method. So having the fetcher on it ensures we have that clear boundary of concern. It helps us maintain clean code. The other great benefit of injection, of course, is unit testing, particularly when you're dealing with things like third-party servers, To use the British idiom, hitting third-party servers is just not cricket. You can't get away with that sort of behavior. So when testing, we can use a mock. We just inject that into the processor. Now, as we inject the mock into the object under test, we can make that mock return whatever we want. We can have it return all the good data we can kind of expect and want to get. We can have it return all the bad data. We can have it even be a failing server. We can make it whatever we need it to be to exercise the code path through the processor or through the fetching. And one thing I would say at that point is having knowledge of your domain, having worked in your domain for a while, will help you understand what the edge cases are that you need to test for. And then using mocks in cases like this allows you to plan those out and test for them and actually code up those edge cases. And it makes, when you identify a new one, it makes the test-driven development response to that new edge case really straightforward because you can make the mock, represent the edge case, and then fix the code and know you're all good. Now, I would say if you do want to exercise actual fetching, and it is quite a good thing to do sometimes, then the HTTP test from the standard library, that is an excellent package for this. And I'd recommend it if you haven't used it. And if you haven't and you want to know how it works, give me a shout later and we'll happily do that. But as an aside here at this point, for the testing part, a few packages we found really helpful. As I've just mentioned, HTTP test is great. But there's also Dan Kinder's HTTP mock. And this, full disclosure, he's a colleague of mine and a good friend of mine, but this takes that HTTP test idea a little bit further, and the setup is really simple and the responses are really elegant. It's a really great library to use. And again, I can take some time later and drill into how that works. I don't have any examples in my slides today. And then finally, I think it was mentioned in the testing talk yesterday as well, the Testify package is great. And you can do all sorts of things with mocking in there, not just mocking servers, but mocking your own interfaces to make sure you're actually focusing your testing in the right spot. It's well worth looking into and having a play around with, pretty much regardless of your architectural pattern, to be honest. So for us, the benefits of interfaces in our context are they've provided us with a simple way to separate concerns and yet implement a cohesive whole. There's no fragmentation, and there's no spaghetti code. Now, within the application, the various interfaces we have define behaviors of components. Now, that doesn't prevent you doing stupid stuff in the actual code. We're all capable of doing that. But it does help you maintain focus by clearly outlining purpose. And that's really good for the code, and it's really good for us engineers when you're kind of building out the next thing. You know what the focus should be. So finally on this one, interfaces are superb for injection. They're allowing you to both simplify production code, as hopefully that quick example showed, but it also helps you keep focused to your testing. And being able to mock responses is useful when dealing with third-party servers or services or other sorts of packages, those external dependencies. Now, we're going to talk about Go routines. I do love Go routines. It's hard to talk about them without channels, but I'll give it a go. The two features, channels and Go routines, they just sit so well together, and you can compose them in a variety of ways to deliver concurrent systems. And having written concurrent applications in a variety of languages, I can honestly say that Go is by far the nicest to do this in. But before we dig into this, if you're thinking about parallelizing an application, stop and think about it first. Think about the data flow that's going on with that parallelization. Draw it out on paper. Just kind of attempt to visualize it. That's going to save you a lot of headache and pain later on. And also pre-optimization, that's a no-no generally. We all know that, right? But definitely in the use of something like Go routines. Concurrency is complex. When it's needed, it is fantastic. But if you don't need it or you aren't sure, I'd say don't do it. Don't make that your first thing. But next up, some examples on how we replaced fragmented multi-instance systems with a balanced use of Go routines. The first thing we've used is worker pools, and we use these extensively throughout our application. And these are a particularly useful concept when the same task needs to be run several times. It's kind of great for fetching data from distinct connections or distinct addresses at the same time. It's great for us running multiple different processes at the same time. And having a worker pool be self-contained makes it easy to reason about. But it also means you can kick off the enclosing function in a Go routine, making your whole pool non-blocking. And that's very helpful. Well, this function snippet here defines a worker pool for us. Now, this function can be called in a Go routine, like I say, making the whole thing non-blocking. And the process provider function here is where the manager struct really takes advantage of the processor interface I showed you. You can call process regardless of the provider type, which is very useful. Now, under our old system, this sort of thing was handled by running multiple instances of an application, and keeping track of those meant an in-house management system. But the fact that this function is called in a Go routine means we can also start another worker pool handling the items that processing providers generates. So we have distinct worker pools, one sending on a CHAN, one receiving on a CHAN, and it means we have clear and continuous data flow through the whole application. Further, this idea gives us easy control over how many workers there are, providing that sort of easy in-app scalability. We can performance tune this. Under our previous architecture, we would just spin up numerous instances of applications and have more of them running. You have more processes to worry about, more things to worry about who's talking to what database at any given time. But with this new architecture, we can simply add to the worker pool. In fact, early last year, we needed to boost our processing rate. We were kind of early days in the application, and we were hitting sort of 50 to 80 items per minute, nothing major. And we needed to go faster. So we needed to hit kind of 500 was the sort of determined benchmark. We needed to be able to process 500 items per minute. We tuned the app by adjusting the number of workers in the pool, re-released it, and hit sort of 750 to 800 items per minute. No extra code changes, no extra instances of the application. We changed one value in a YAML file and restarted. And that was that. Now that, for me, proved that the monolith was a good choice for this application. I didn't have to worry about deploying multiple things. I didn't have to worry about configuration across multiple instances. I could tune the whole app in one go and then re-release it and know that it was all going to be fine with one another. Didn't have to coordinate different releases or different uptimes or downtimes. That was very, very useful for us. The other thing we do with Go routines is what we've called out-of-band processes, sort of tasks that are kind of ancillary to the main application. So using Go routines for these means that they don't impact on the main focus of your app, but you also don't have to worry about deploying them separately or configuring them separately or managing them in any way because they're just part of the app. This approach has meant we don't need kind of separate apps for tidying things up, which we did have previously. This is also the building block for replacing all of our crons, but I'll come onto that a little bit more when we talk about channels. But as a quick example here, we obviously download data from remote sources. That's kind of where we get all our content from. And we then keep the original sources on disk for 6 months. But then it does have to be deleted. We've got to get rid of that stuff after 6 months. That's kind of part of the deal. Now, what we do here is we have a function called clear old items. Obviously, the details aren't really that important. It's an infinite loop that walks over a file structure, deleting stuff that's older than 6 months. But it's a small Go routine. And a small Go routine will happily just run forever. You can just leave this thing doing its own thing and not worry about it, which is great for these sort of simple tasks that you kind of want to make sure are happening, but you don't want to worry about deploying separately. Just put them in the app, in a Go routine, done. So the benefits of Go routines for us are that we can parallelize various parts of the process. We have asynchronous processing of different stages of the pipeline. And we have a way to handle our out-of-band processes within the application without the need for separate crons or separate scripts anywhere. Now, we talk about channels. But before I do, I need to sort of explain to you how we move data between all our different processes. So as you saw in that architecture, there's lots of different boxes doing lots of different things. And the way that kind of worked before was we had kind of one or more instances of one or more apps that would read data from one or more sources and write it to the database. Then we would have one or more instances of one app and one instance of another app that were all reading from that database, writing to the index buffer, and writing back to the database. And then we'd have one instance of one more app that would read from the index buffer, write to the index, and write back to the database. Yeah, I think that's right. But we now have just one app that reads from our source, writes to the index, and writes to the database. And a key part of achieving that simplicity for us is channels. We replaced a host of poorly communicating systems. Never communicate through MySQL, please. But we've replaced all that with a monolithic application that just communicates internally across channels. So the use of 2 channels, along with Go routines, defines our data pipeline really clearly for us. A clearly defined data flow or pipeline is essential in any architecture. And what we found is that Go enables us to define this very clearly and robustly, even within a monolithic application. We have a clear pipeline with no spaghetti code and no overreaching dependence. So within our application, we have this central component that I've mentioned a few times now, this idea of manager it's really just the controlling brains of the whole thing. And this component defines these channels. It sends and receives data on the channels. It passes the channels to processors when necessary. The manager is responsible for controlling the entire data pipeline. It defines both the channels. So on instantiation, we create those and then just pass them to the functions that need to send or receive on them. And you can pass the channels kind of directionally, which is really cool. So your function's only going to write to the channel or it's only going to read from the channel. That's really useful to do. So this code snippet here shows how we've used Go routines to define the data pipeline. And the channels defined here are just the conduits through which the data flows. We're sharing memory by communicating. Now, using Go routines for the first parts of this data pipeline and a blocking call for the final stage means we can continually be processing data all the way through to the final stage. That final stage is blocking. It's continually ranging over the item channel, which means this is a long-running app. And we can easily shut down the application by closing out the channels and letting them all drain. And then the blocking call will finally return and we'll exit. But most importantly for us, the full flow is now defined in 5 lines of actual code. I mean, that's it. That's the full flow of the whole application. Right there, 5 lines of actual code. So you can see that at a glance. You can understand where the data is going to move. And this was an important consideration for us in choosing the monolith architecture style. It's clear. It's easy to reason about. It's right there in front of you. Now, the provider channel is populated with details of providers. We just have a function continually reading those details out of a database and feeding them onto the channel. And this snippet shows that continual range over the provider channel. Obviously, there's some details missing to make it fit on the slide for everybody. But having a centralized channel means that the pipeline which sends and receives on the channel is clear and obvious. And we can see here that we're simply receiving the next provider on the channel, calling process provider, and moving that onto the next step in the data flow. If you recall that the processor interface defines a process method that takes a channel as one of its parameters, as we hit process provider, we'll call the relevant concrete implementation of this interface. This then generates item records for us. It kind of from the provider source. It goes and grabs the source, parses the data, gives us the content item records, and then all those items are put onto a shared item channel, moving the next piece of data along the pipeline. So we're continually working through this pipeline, but with the interfaces, Go routines, and channels, this remains clear and well-bounded. Now, with each processor sending data on the same shared item channel, we can easily centralize the next step of the flow within Manager. The dispatch item method controls a worker pool, where each worker ranges over the item chain, calling the process item function. That's the final step in our workflow. Now, we have data moving through the pipeline. We're then processing items for a variety of different sources in a completely consistent manner, something we weren't achieving before. But we're also doing it without really needing to know the details of the provider at the point at which we process the items. Also very helpful. And it was that combination of channels and Go routines that got us that simple in-app scalability that we talked about before. Now, comparing this to distinct apps to handle overlapping parts of the pipeline, we can see that our previous architecture lacked this consistency. We had unwritten rules that were just lost and not obeyed, causing all manner of problems that are hard to debug when things go wrong. Now, if this were completed with microservices, there would probably be a queuing system in place. I mean, that's not unlike what we had before. Though, as I've said, hopefully nobody's queuing in MySQL these days. Or, we'd have introduced a lot of HTTP calls around the place. And neither of those are as simple or as effective as the channels-based communication we now have for this problem. It's also conceivable that under the microservices approach, we could have had multiple services writing to the database. Now, That could lead to data confusion as boundaries of responsibility get blurred. Or it could lead to extra latency maybe, as we have to introduce a database layer that you kind of everybody communicates through an API to talk to the database, just to keep things consistent. Well, moving on from data flow, channels have numerous other uses for us, not least of which is as a semaphore. Now we have a requirement from one of our data providers, and don't try and understand the requirement, I can't wrap my head around it, but they don't want us to make more than 10 simultaneous initial data fetches. I tried to talk to them about it, but that's just the way it is. But handling that in Go is a breeze. So under the old architecture, we got around this by this issue by manually starting a distinct application to just do all the fetching. So you had one instance fetching all the data, and then we started off multiple other applications to parse what came out of that fetch. So we were only ever processing one fetch's worth of data at any one time, regardless of it being an initial fetch or a subsequent fetch or whatever. So what we do now is when we create the new processor in Manager, we instantiate a buffered channel. It's easy for us to determine then if a specific fetch is deemed initial or not. And if it is, we just send an empty struct on that channel. Well, that's obviously a blocking call. So if that blocks, there wasn't enough space and we're already doing 10 fetches. When that does get allowed, you can put that on, move on to fetch, run your initial fetch, and then receive off the channel. And the empty struct is a great thing to use in these contexts because it essentially compiles down to nothing. So it really does make this flow really nice and really easy to reason about. Now, using the channel as a semaphore now, we can obey their restriction without needing to rely on the manual processes and without needing distinct applications. Handling this limitation is really part of the concept of processing data. So it does belong in the processor. It doesn't really belong in another application. Now, cron replacement. I did hint at this a little earlier. I was quite excited about this when we first did it. It was quite a simple solution to a problem we had. But under our old architecture, we had a distinct set of applications and scripts that were run with cron jobs. And the biggest issue with cron jobs, and I'm sure I can't be alone in this, is you either forget they're running, or you misconfigure them, or you move servers and forget to start them up at all because there's no record of what they were, and then that's just lost. Maybe I am the only one, but that definitely happened to me. So what we do here is we use what's called the select for pattern. So you have this infinite for loop, and at the bottom of that, you have this select case. Now, the key part in the cron replacement is the time.after. So we want to just check our clearing old items every 12 hours, which is what this will do for you. Now, I grant you that's not the same thing as a cron. You know, a cron you can specify to run at 3 o'clock every Tuesday, for example. You can't do that like this. But what this has done is remove a significant pain point for us. And the trade-off of that, kind of just check every 12 hours for really old stuff compared to a cron running something, is definitely worth it for us. Now, we also had separate applications for other things, like some sort of database management stuff. So you then ended up with duplicate database connections in multiple kind of code bases, often in multiple languages, which wasn't even indicated before. That architecture was in more than one language as well, which made it even worse. But now we keep all the code in one app. So it's naturally all in the same language, which is obviously Go, the best language there is. Now, it's then deployed with the app. It's then turned off with the app. And the database management and file system management is all just in one place. We don't have that duplication across different code bases. But we've managed to keep everything contained, and we've avoided fragmentation by using these distinct Go routines. So the benefits of channels for us. We've used them in a variety of ways in our code to help with the data flow of the application. Now, the data flow was initially whiteboarded out. There was a few of us stood at a whiteboard for a while and drew out how this thing was going to work from a data flow perspective. We then translated that into code, and that translation was really simple. We have no reliance now on external services or databases for communication or pipeline management. That's definitely a win. And it makes understanding the data movement now really easy for us. And then when we were asked to restrict the number of requests we were making, we use a buffer channel as a semaphore. That hopefully showed how simple that is, but it also shows you can use channels outside of Go routines. They are useful by themselves. Now, along with the out-of-band processes we saw before, the kind of select for pattern and the time.after channel has meant for us no more crons, which has removed a significant pain point for me, which I'm happy about. So, if you recall the architecture we started with, with Go, using interfaces, Go routines, and channels, we've reduced the fragmentation. Each of those fragmented parts of the architecture has gone away. We have a single cohesive whole. We now have one application that is well-defined and clearly understood. It handles the full data process from start to finish. We've removed the fragmentation we once had and still maintained correct focus of concern and orthogonality. All the distinct applications replaced with a unified monolith that allows us to control data flow accurately and deterministically. It's given us a clear, simple insight into the application, and it provides us with a far better solution to our original problem. So, the monolith is a useful architecture. It remains useful. But, like any architecture, it does need to be used in the right place, and it does need to be used with care. Now, there are certain lessons that apply to microservices and monoliths. Know your data flow. Define your boundaries of concern. But once you have the data flow and the boundary of concern, you can control a manager or to kind of handle running that pipeline and ensure that data is moved as required and all of the components that we have are used correctly. That gives you a certain level of assurance that the data you care about is moving through the full system in a timely manner. And when you know that the data you are processing has to make it all the way through the different stages in a timely and deterministic manner, in a set order, then you have a good fit for a monolith. The issue with a microservice for this sort of application is that you introduce a number of extra complexities. Inter-service communication, service availability, distributed tracing, being just a few of the concerns or complexities that don't exist under the monolith approach. Go provides us with a number of primitives that are very useful in the monolith. And hopefully this talk has shown that the monolith is not to be feared, pitied, or shunned, but used wisely, and it can be an architecture with retained relevance. So, thank you for your time. If you have any questions, we have some time. I can attempt to take them now. Or if you want to chat further, feel free to grab me later. Reach out on Twitter or Slack. I'm always happy to help, and I'm always keen to learn from your perspective on this. So thank you very much. Oh, at the back over there.
How do you handle adding new providers?
Okay, yeah, that's not covered under this talk. You're a good spot. So basically, what we have for handling our new providers is we have a simple database table. So we simplified our data model quite a lot. So the old data model, which I couldn't even begin to explain, had far too many tables in it. The new one just has a list of providers, that's one table, and then a list of items, that's kind of the metadata we're tracking. So when you add a new provider into that table, and it's of a particular provider type, and it's those types that marry up with the processor. So then we say, okay, this is an independent type provider, it hits the independent processor, or this is I can't actually name all the others, because we give too much away, but independent is safe. So yeah, it works off the provider type, and you just add new records into that table. Okay.
Store? Any questions next door?
Oh, okay, well, like I say, feel free to grab me later if you want.